For day two, the goal for today is an introduction to statistical investigations and the logic of statistical inference. I would suggest taking a moment, pausing this, and reviewing day one, just going over the terminology and make sure you're comfortable. Throughout the rest of the course, a lot of times we'll be looking at various studies. In this case, we're looking at a study regarding with a chimpanzee. Here, the research question is told to us, can chimpanzees solve problems? So pause the video for a moment and take a read over the study. Okay, so what happens is they were curious whether a chimp can solve problems. And the chimp that they used in this case was named Sarah. And she was shown a videotape and then presented with two photographs with one of which depicted a possible solution. So in this example, the little girl here is actually on a boom box. Now, for those of you probably have seen a movie with a boombox in it. Yes, that's what I used to listen to for music. They were big. They took, I don't know how many D-sized batteries, but with headphones, I think it saved my parents' lives. Anyways, two photographs. She's trying to listen to music and it's unplugged. You see the little plug here. And the other one just shows something plugged in. And Sarah had to choose based on the videotape. She saw that someone couldn't hear. And out of the 8 problems that she was presented with, Sarah picked the photograph with the correct solution 7 times. 7 out of 8 sounds pretty good to me. But we can't say much about that yet. So let's start with identifying the observational unit. Now, I'll be honest with you, even when I started studying statistics, the first thing I want to say is, it's Sarah. Well, remember, when we're looking at observational units, we're looking at the individual things that on which data are recorded. So we're not recording data on Sarah per se. What we're looking at is when she looks at each question or each problem that she is given or each videotape where she looks for solutions. So I'll write each question that she's asked or each problem that she has to try to solve. Now, the variable is where she watches the videotape, and then she has to decide, she has to pick between one of the 2 pictures. The variable in this case is whether she chooses the correct photo or not. So I'll just say correct or not. Whether she chooses the correct photo or not, would that be categorical or quantitative? If you think about it, it's obviously categorical. And correct or not, would we say binary or not? Hopefully immediately you think binary. So now, what is Sarah's proportion? Obviously, as we talked before, it has a number between 0 and 1 of correct answers. 7 out of 8. This class always use a calculator, don't worry. I did not do that on the top of my head. I already had the answer. But 7 divided by 8, so 87.5% of the time she correctly identified. So that's a pretty high percentage. Is the number in 3 a parameter or a statistic, and how are you deciding? Okay, so it's based on a sample, right? She did a run through. I'm going to say statistic. Because it comes from a sample. Did she get the answer correct the majority of the time? Yes. Because 0.875 is greater than 0.5. So she's doing better than half the time. So let's just sketch a quick bar chart to display the distribution of the correctness of Sarah's answers. I always want to make sure that we label. So I'm going to label this side the proportion because that's what we're going to record. And we know that she got it correct 0.875 or 87.5% of the time. And then if she got it, so I'm going to do the first bar, which would obviously be the tall bar, and I'm just going to label this correct. And overall, these are Sarah's answers. If she got it correct that much of the time, we know that she was incorrect for a bit of it. How often was she incorrect? Well, we know it has to total to 1. So you can take that difference there, and this is 0.125. What are possible explanations for Sarah getting 7 out of 8 correct? Pause the video and think a little bit about it. So one of the options, and you can pause the video and write this down if you like, and then get me going again. So Sarah tends to guess. So one of the possible options, and she's got lucky. She, can you flip a coin 8 times and get heads 7? Sure. Or another option is she knows what she's doing, and she's doing better than just guessing. Or the study was poorly designed. For instance, they always put the correct picture on the right side, and Sarah tends to use her right hand and grabs the right one. We would assume that since this is a study, well-respected, published in Science magazine, that they would have a well-designed study. But this is something I want you to keep in mind, that studies can be poorly designed and you'll come with a bad outcome. So let's assume in a well-designed study, which this was, the only 2 possible explanations for the observed results of the study are, and I want you to think about, what could you write down? And pause the video, think about it for a second, and then get it going again. Okay, usually what we're going to do, and this is something to keep in mind, is the first option is going to be nothing interesting is happening. Sarah just tends to guess. So it's just guessing, nothing special is happening. And this time she got lucky. So that's option A. So in general, as you go throughout this, you're going to notice the first thing we assume is that nothing interesting is happening. What from the study we're hoping to find, though, is that Sarah knows what she's doing and does better than just guessing. And that's option B. So that's the way we think about it. First option, nothing interesting is happening. And the study just, we didn't find anything that supports that actually something interesting is happening with our study. Which explanation do you think is better, more plausible, more reasonable? Do you think she's just guessing? I don't. I'm guessing, yeah, here we go with the guessing again. B. B seems more plausible to me. But how would you convince someone who is skeptical that the other explanation is not a reasonable explanation for Sarah's observed results? So how would we convince them? So this is, we're going to go down to number 10. Describe how you can use an everyday item to convince the skeptic that random chance is not an explanation of Sarah's results. So each time she has to pick between 2 pictures, and if she just guesses, she could get it right or wrong. So what is something that we have, well, or actually I have a shortage of them right now, but that we have, I'm sure you have one with you somewhere, that we could use that gives us 2 options. Hopefully you're thinking coin. So at this point, pause the video, get a coin if you don't have one. I'm going to do the same. Okay, hopefully you have a coin now. So the coin toss, remember it's 50-50. We're assuming most coins are fair. So we can simulate by chance with a coin flip. We're going to let heads be correct. So if you want to pause the video and write this down and then listen, that's great. What you're going to do to simulate what happens is you're going to toss the coin 8 times in a row and record how many times you get heads. And then you're going to repeat this 8 times coin toss and recording the proportion many, many times. Then we'll compare her actual performance to what we would get after many, many iterations of this. So we're going to be looking at modeling the long run pattern. Long run, because remember, when you flip a coin, it's 50-50. You can get heads or tails. You could get, you could do 8 flips and get all of them be heads. But remember, when we're talking about a fair coin and we toss it many times, we're not worried, but we're worried once again, we're thinking about what the long-term pattern is going to be. If you do an infinite number of these iterations, ultimately you would think that it would center around 0.5. In other words, 50-50 chance. So looking at the note, thus you'll be modeling what the long-term pattern of Sarah's score could have looked like if Sarah were just guessing which photograph to pick. We're going to use coin tosses to simulate these results and then compare these simulated results to Sarah's actual observed score to decide whether just guessing that explanation is a reasonable explanation for Sarah's performance. So what I'd like you to do is we're going to carry this out. So 2 trials. We're going to flip the coin. Now remember, Sarah had 8 problems that she did. So we're going to flip the coin 8 times and then record the number of heads. And then you're going to do that again. So take a second and do that. I came up with, in one case, 4, and in one case, 3. Okay. So I have a previous stats class. So I carried this out. I got my numbers here, but here's a dot plot from a previous stats class. So if we were live, we would actually do this up on the board, but obviously we're not live. So where would your dots be on this graph? So my dots, 3 would show up here, and my 4 would show up right here in the middle. So that's where I'm looking at. Now I'm looking at this dot plot, and I noticed that it really tends to center around 4. 4 is the biggest, 4, 5, 3, those all seem like reasonable potential outcomes. Sarah, though, on the other hand, had 7. So that's kind of out in the tail. So we're going to talk about that more as we go along. What were the most common outcomes for a number of heads in the coins? Does this make sense? So I look at it, the largest number of outcomes was, as I mentioned just a moment ago, was 4. And that makes sense because by chance, alone, by chance alone, so chance is just working with a fair coin, it will land on heads about half the time. In the long run. Now remember, we're always talking here about the long run. What's going to happen as we do these again and again and again and again? So the probability of getting heads when we toss a coin is 0.5 or 50%. So on 8 coin tosses, we expect to get 4 heads. Why didn't everyone get 4 heads on 8 coin tosses? Why the variability? Think about that for just a second. So by chance alone, a fair coin will land on heads about half the time in the long run, but it's not always going to happen. So there will be variability just due to chance, random chance. Like I said, if you flip a coin, you could have, in the long run, half the time it'll be heads, half the time it'll be tails. But we're talking very long run, millions and millions of flips, but in a flip of set of 8, you could even end up, in theory, with 0 heads. Is that likely? Not really, especially when we compare it to our draw. No one came up with full 8. No one came up with 0 or even 1 heads. Only 2 people had observations that were 7. So why do we need to repeat the set of coin tosses? Why not just look at one set of coin tosses? So why not just look at one set of 8 causes? Because we want to generate what happens in the long run. We want to get a good idea of what possible outcomes can happen in the long run while accounting for the variation outcomes that's possible by random chance alone. Random chance by chance alone. So on the dot plot in part 12 above, indicate where Sarah's actual observed result is. And based on the dot plot, would it be surprising to get 7 out of 8 by just guessing? So I'm going to scroll back up, and we already looked at that. 7 out of 8 is really in this tail over here. There are very few who got that. So I personally would say, yes, it's very surprising. 7 heads were the correct, because we indicated that was the correct, was heads. Out of 8 tosses, in this case we use the tosses to represent the questions, looks like it rarely happens. By random chance alone. Seven is far out in the tail of the dot plot. Now, that's nice, it's helpful, but wouldn't it be better to have a lot more of those repetitions to see what happens? So if you want to study the long run pattern, you should look at more trials than what that class had done, each of 8 coin tosses. You could flip a coin like you did earlier, but if you wanted to do that 1,000 times, it would take a long time. So this is when, remember I showed you earlier those web applets. We're going to actually do one of those right now. I'd like you to also run it after you watch this and see what you come up with. It should come up very similar to what I come up with. So I am going to pause for a moment and get that set up. So I went to Canvas and went to the web applets and clicked that. Remember, you have to click, it shows up all as red and you have to click web applets. And this is what it looks like. I will in general tell you which web applet you should use. One proportion is, if you look through, obviously where I've clicked, these are the ones that we're going to be using a lot throughout this course. One proportion is the one proportion inference. So I click on that app and it says right away the probability of heads is 0.5. So we're going to simulate a lot of repetitions. So does this make sense, the probability of heads? Yeah, because we're thinking about a fair coin, 50-50. Now, as we go through, how many tosses did we do? What was our sample size? Well, it certainly wasn't 5. What did we do? Sorry, I had to turn my keyboard on there. So how many tosses did we have? Well, we had 8. So we're going to do one repetition. So we're going to pretend we're flipping a coin 8 times. I'm going to now draw samples. So it's drawing my sample. It's doing the coin flips for us. And it shows on the dot, here we go, there's our heads. And it had 6 heads and 2 tails. Okay. So we would record that in our on our sheet, but I want to keep going and show you more how this looks so that you'll be able to record your answers when you go through and do this. So let's say I wanted to record, so that's one sample. All right, 6 is pretty high. Let's say, should we do it again? Sure. So we're going to draw another one. See, we now have a total of 2 samples. Already, so the second one came up and this time we had 5 heads. Alrighty, I'm going to do that again and you're going to notice that it's plotting as we go along. Oh, this one had 4. Oh, you notice that the total number of times that these are called repetitions. So each time I have one repetition, it's flipping the coin 8 times. So I do that again. So I have a total of 5. You'll notice then there are 5 sets down here. So each of these represents how many heads I got when I went through this. But we want to show what happens if we flip it a lot of times. So this next one, I'm going to change it to 995. And now I'm going to draw my samples. Looks a little different now than what we had before. I'm also going to click Summary Statistics so we can see mean, remember, is our center. Our center's 4. Well, that makes sense because remember, we think it's going to be 50-50 and there's 8 repetitions. Now, when we were looking at this, I'm just going to show you this now. Number of heads. How many did Sarah have? Well, remember, she had 7. So I'm just curious how many of our repetitions ended up with more than 7. Ooh, only 32 out of 1,000. That's not very many. Okay, well, I wanted to just show this to you so you could see what it looks like. Now, this is my distribution. You're going to do this as we go along throughout the course. At this point, the tool I use is called Snip. I'm just going to show you. It's called Snipping Tool. So I don't know if you have that or if you can get it. But the sweet thing is I can literally just, let's say I asked for I wanted a copy of what you had. I went and it grayed out the whole thing. I snipped this, and now I automatically can just paste this into my document. So I'm going to pause for a minute and go back to our notes. So back to notes. We had gone and used the one proportion test. I'd like you to do that on your own and fill in your answers here. So I filled it in just so we can talk it through to make sure you understand. So the probability of heads is 0.5. It makes sense because we're simulating what happens by chance, and by chance alone there's 0.5 probability of heads. Now, what if we had something that had 3 equal opportunities to be true? Could we use a coin? No, but they have something called a spinner, which we'll see later in the quarter, where you put the probability as being 1/3, 1 out of the 3, which would be 0.333. So then we had to do a single repetition, and you would record your answer. I think mine was 6. Complete the following. In this simulation of the method, randomly picking an answer for each of the 8 problems, the answer was picked for whatever you got correctly for however many problems. This could have been is less if your answer is close to 4 than the observed 7 out of 8, because whatever that, let's assume that up here you got your answer. Let's say, for instance, 6 is a bit, I got 6. Was correctly picked. In my case, it would be for 6 problems. This is less if 6 is closer to 4, and it is. 6 is closer to 4, extreme than the observed 7, because 6 is closer to 4 than 7 is to 4. So we did then the drawing of the 4 more times, and I didn't record them. I had my other machine going there. Did I get the same number of heads each time, though? Obviously, no. I want to say we had 6 and then 4 and then 5. Does it surprise me? Absolutely not. Because there's going to be variation from one set of tosses. Sometimes the set is called one set of repetitions. You'll notice that in the applet it's called repetitions. So one set of repetitions of 8 tosses to another set of 8 tosses. And then we entered 995 to come up to a total of 1,000, because remember, it keeps adding them. If you want to start fresh, you'd want to click reset in the app. So I have a screenshot, and I use snipping. I did not include that here. You should snip yours and put it in, but you can at this point. You don't need to. I just wanted that to be an option for you. With regard to the dot plot, how many dots are there total? So what we generated, how many sets did we run? It was 1,000. So we obviously have 1,000 here. Once again, this is just why do I have this all written out? It's more for review. We've done this before, just talking you through to make sure you understand. Each dot represents the number of heads, which we're using for correct answers out of the 8 tosses. And the tosses are the number of questions, problems, where she had looked at the videos and had to choose. And then we're looking, because we're curious how it compares to chance alone. So based on the dot plot that shows 1,000 possible results that could happen if she was just guessing, does a result such as 7 appear very surprising, somewhat surprising, or not surprising? Well, we saw that 7 was far out in the tail, right? So it's rare that it would happen. Based on our findings so far, which of the following statements is accurate? This proves that Sarah does better than just guessing, or this provides strong evidence. Now, I want to right away say we don't prove things. We hope to find evidence to support our claim, but we don't prove them. So if in a true false or whatever you say, this proves something, yeah, we're not into proofs in statistics. That's not what we're looking to do. So let's explain what we have. It's possible that Sarah got 7 correct just by guessing, but it looks like it's very unlikely to get 7 correct just by guessing alone. So we have strong evidence, but we've not proved that Sarah in general does better than guessing. So I'll bring that screenshot back up in a moment. But suppose that Sarah had picked 5 answers correctly out of the 8. Based on the above graph from the applet simulation, which I'll show you in just a moment, if Sarah tends to just randomly choose a photograph, would a result of such as 5 correct out of 8 be very surprising, somewhat surprising, or not surprising at all? Explain how you're deciding. So write down what I have here, which is just saying 5 out of 8 doesn't look that very unlikely. You could do it just by guessing. So I brought back up the graph that we the plot that we came back up with. And we see here that 5 has a lot there. It is not unusual to have 5 out of 8. 3, 4, 5 all look like reasonable answers. 7, 8, those look like they're called being in the tail. And we're going to talk a lot more about that as we go along in the course. Once again, you can see in the upper left-hand corner of this snipping tool. It's a great tool, and I will show you how it gets into the actual document in the future. Sorry, I didn't do that this time. Have a great day, and don't forget after this to review and then take the quiz.